Okay, hi everyone, welcome back. So this is the second talk of this morning session. So we're very happy to have Michael Kastoryano from University of Copenhagen and also Amazon Web Services to give the second talk. The title is Mixing in Space and Time for Quantum Gibbs Sampling. Please, Michael.
Thanks a lot. Thanks for the invitation, and I'm really sorry I couldn't make it out to be there in person. I was asked to give a bit of an overview talk, and that sort of works well because Andras gave a talk on our joint work earlier in the conference. So there's not much other novel work. On the other hand, I want to talk a little bit about, not so much about quantum algorithms, but mostly about a mathematical challenge of open quantum systems, which I think with the new developments in quantum Gibbs sampling algorithms is starting to become relevant again. So I want to start out sort of soft and give some physical motivation for these results. Now, thermal phase transitions are apparent in everyday life in all sorts of forms, right? And in the 18th century, we developed empirical thermodynamics to describe them. But then early in the 19th century, or late in the 19th century, statistical mechanics was developed to try to describe certainly spin systems. And they were very successful. They could also describe certain elementary phase transitions, but statistical mechanics in its basic form gives a very static picture of the systems of interest, right? It gives probability distributions of different configurations. And then sometime in the middle or second half of the 20th century, Glauber came around and gave a dynamic description of the thermal evolution of spin systems. And this was really quite new. So the point, and since then, there's been a really extensive body of mathematical results, mostly in classical statistical mechanics, that tries to combine the static pictures of statistical mechanics and then the dynamic picture of Glauber dynamics. And this talk is an overview of what is known classically from a fairly high level standpoint. It will be technical, but it can get a whole lot more technical. And then I want to discuss what we can expect from this theory in the quantum setting. So the picture you want to keep in mind is the Ising model. A lot of these results extend beyond the Ising model classically and quantum mechanically, but it's most convenient to think of the Ising model for most of what I'm going to say. So just as a reminder, the Ising model is a simple classical Hamiltonian that gives an energy penalty when neighboring sites have a different sign, and no penalty when they have equal sign. And the system in 2 dimensions is known to have a phase transition at a critical temperature. Below the phase transition, the typical states of the system are going to be either all up or all down or something close to that. And above the phase transition, the typical states of the system are going to be completely mixed. And then at the phase transition point, you're going to have polynomial ranged correlations. The point of the phase transition is known. Mathematically, the way we want to characterize what we mean by correlations is looking at the covariance. And here, I'll ask you to try to remember this particular notation because I'm going to use it a lot during the talk. So we'll say the covariance between F and G. F and G are to be understood as local observables, in this case, classical. And the covariance is the inner product of F minus the average of F in the state pi. Pi here is going to be the Gibbs states, the classical Gibbs state most of the time, and G minus the average of G in pi. And this is an inner product weighted by pi, right? When we say that 2 observables F and G are not correlated, so have exponential decay of correlations, classically, typically what we mean is in a very, very strong sense, meaning that the F and G don't have to have point volume, right? They can have a very large volume on a 2D lattice, meaning they can be 1/3 of the lattice each, but as long as there's a distance between them, the correlation between the first third and the third third of the lattice is going to be exponentially decaying, right? So it's sort of a very strong form of correlation decay that we're going after. And in particular, for the Ising model above the critical temperature, even that very strong form of correlation, where F and G can be macroscopic, is going to be exponentially decaying. Below the phase transition, you're going to have long-range correlations. So to set the stage a bit, I know it's been introduced at least in one other talk. I'd like to remind you of the Metropolis-Hastings algorithm, which is the most common algorithm used to simulate statistical mechanical systems. And the idea there is you start with so you have a Hamiltonian describing the energy constraints of your system. On a graph, for us, we're only going to be considering lattices. And then the Metropolis-Hastings algorithm is built in 2 steps. The first step is to choose a symmetric transition matrix. And this symmetric transition matrix is typically going to be chosen ergodic. The simplest example on a lattice is you just pick a spin and you flip it. And then what you do is after a spin flip, you'll look at whether the energy increased or decreased. If the energy decreased, you'll accept the move. If it increased, you'll accept the move, but only with a certain probability, which scales as the ratio of the 2 Gibbs states or the exponential of the energy difference. What's special, among other things, about these update rules is that they satisfy detailed balance, and we'll get back to that in a second. If T is ergodic, then you're guaranteed that the Gibbs state is the only stationary state of the probability transition matrix T. And in some circumstances, it's going to converge rapidly. What we're going to be interested in is the continuous version of the Metropolis-Hastings algorithm called Glauber dynamics. And instead of a stochastic matrix, what we have is a dynamical semigroup. So for every positive time t, e to the tl is going to give a probability transition matrix. L is the generator of the dynamics. And stochastic matrix is going to have rows summing to 1. L is going to have rows summing to 0. And typically, the off diagonals are going to be real and the diagonal is going to be negative. But the way you build Glauber dynamics is in a sense quite similar to the Metropolis-Hastings algorithm, which is that you start with a symmetric exploratory generator L, which can be understood as the Laplacian of a graph. And then you modify L with this rule, with the following rule. This guarantees that the dynamics for any value, for any positive time t, is going to satisfy detailed balance. Now, detailed balance is a convenient mathematical property of a Markov chain, which guarantees that the state with which it satisfies detailed balance is a stationary state of the Markov process. And it also guarantees that the spectrum of L is real. Okay, so we have, in particular, the spectrum of L is going to be non-positive. So if you have a unique stationary state, the stationary state is going to have eigenvalue 0, and the next state is going to have eigenvalue strictly negative, positive, real and negative. And the difference between, well, the magnitude of the second eigenvalue is the spectral gap of the process. And even originally, Glauber introduced these dynamics as a way of mimicking. I'm not sure how he came to this conclusion or to this interpretation, but it was, in his mind, a way of mimicking thermal interactions with a thermal bath. So the main mathematical result that I want to talk about is this space-time mixing theorem. So what I mean by space-time mixing theorem, it's employing the classical terminology. So mixing in time means that if you start with any probability distribution Q over your system, so any configuration Q, and you time evolve your system with PT, then it's going to converge to the Gibbs state in a time which scales as an inverse constant, which is related to the spectral gap of L, and the logarithm in the volume. So that's the strongest form of convergence to stationarity that you can consider. What it means is that an observable F is going to time evolve, and you can think of a Lieb-Robinson bound that's expanding out, but it converges so rapidly that the Lieb-Robinson bound doesn't have time to get very far before the dynamics completely freeze, right? So another way of understanding this is that the dynamics relax locally. You can't have excitations that are transferred from one side of the lattice to the other in the natural thermodynamics. The other equivalence is decay of correlations. This is what we're very familiar with in physics, right? And the particular formulation of this is in terms of the covariance. So we say that the covariance between two distant observables, F and G, is going to be decaying exponentially in the distance between F and G. And although I drew F and G as being local quantities, again, they can be quantities proportional to the volume of the system. And in fact, this is a very, very strong theorem because it provides a double exponential separation in the following sense. If you consider, well, at least in the time sense. So if you are above the phase transition, the thermal phase transition, at sufficiently high temperature, your system mixes in a time which is logarithmic in the volume. If you're below the phase transition, your system mixes in a time which is exponential in the volume. Okay, so you have a double exponential separation between the two. On the decay of correlation side, you have either exponential correlation or flat correlation, right? At the phase transition point is obviously a very interesting point where you get polynomially decaying mixing time and polynomially decaying correlations. On top of that, this equivalence actually has been expanded to many, many different types of formulations. So, and I'm introducing this not as rigorous mathematical statements, but there are some relatively weak conditions which connect all of these properties. So rapid mixing is one. Poincaré inequality, which in the case of detailed balance generators is the same as a gap inequality. So the existence of a spectral gap independent of system size is equivalent to a log Sobolev inequality, or at least the log Sobolev inequality implies the Poincaré inequality, is equivalent to this condition which is called hypercontractivity, which is the contraction of a LP norm from 2 to 4, being smaller than 1. Turns out that the log Sobolev inequality is an infinitesimal formulation of hypercontractivity, which is equivalent to the decay of correlations, and for most systems is also equivalent to the decay of mutual information. And in the classical setting, this is not an equivalence, but there's a form of boundary condition independence. So it doesn't matter really what's happening at the boundary of your Gibbs states for a finite volume, the bulk is going to be behaving the same. Okay, so it's really a web of very strong equivalences. The next couple of slides are going to be very technical. I don't mean for everyone to follow exactly what the reasoning, but I want to give an idea of the proof of this statement so that you get an idea of the ingredients which might be necessary to have a quantum proof, the same statement. So the exact statement we want is that the spectral gap of L implies decay of correlation, implies factorization of the variance. I'll explain what that means, implies the gap. So they're all equivalent. So decay of correlation Okay, and now the formal definition of a gap that I'll be using is the infimum over all observables of the inner product of f and minus the generator divided by the variance of f. The variance of f is just the covariance of f and f. And we'll be working in the Heisenberg picture, where we time evolve observables. And the way this works is very similar to what's been done already a long time ago in Hamiltonian complexity, which is that you take the covariance between f and g. So remember that what we're trying to bound is the covariance between f and g when they're far apart. We add and subtract a constant term. So a time-evolved observables, ft and gt, triangle inequality, and we'll bound each term independently. So the first term can be bounded by this expression, which simply follows from the variational expression for the gap. And physically, what it means is that past a certain time, your time-evolved observable is going to be proportional to the identity. And this time is going to be short. Well, it's going to be proportional to the inverse gap. And the second term can be bounded by a Lieb-Robinson type bound, right? So as long as ft and gt don't move too far away from each other, you get that they're exponentially uncorrelated because of Lieb-Robinson type bounds. And then if you take the minimum t, the t which minimizes the right-hand side, you end up with a covariance which decays as some constant, well, exponential of some constant times the distance between f and g. Okay? This isn't part of the actual theorem, but to relate it to mixing times, what you can get is the one norm between PTQ minus the Gibbs state can be upper bounded, and this comes from LP interpolation theorems, by the 2 norm times a constant in front. The 2 norm can be bounded by the gap, just by, again, the spectral definition of the gap. So the inner product is related to the 2 norm. And the constant in front can be bounded by an exponential times the volume, right? So that you get this mixing time bound, which scales, and this last term can be bounded by 2. So you get a term which is exponentially decaying in time and proportional to the gap, in the inverse gap. And then a term in front, which is exponential in the volume, right? So that gives you polynomial decay or linear in volume mixing time. The log Sobolev inequalities gives you this sharper logarithmic mixing, and it's a lot more complicated, but suffice it to say that instead of using the variance, you're using a type of relative entropy function. The second part of the proof, factorization of variance implies gap, might be a bit less familiar. So to define it, what we need to do is we need to define a local gap. So we need to consider what happens on a lattice if you imagine the full lattice being finite but very, very large, and you just look at a single patch A, right? Contiguous patch A, where you can define the local gap of the model on A by defining this inner product of the generator only on A. Remember, the generator is a sum of local terms divided by the variance of A. Now, this variance of A is given by the inner product of F, and instead of the expectation value of F in the Gibbs state, it's the conditional expectation on the region, which means you project onto the Gibbs state inside the region, but dependent upon what's happening on the outside. And you can show that, in fact, this is a well-defined quantity and it doesn't go to 0. It's typically going to be finite for a detailed balanced ergodic process. Factorization of the variance means that the variance on AUB, so here is a bit funky notation. What I mean by A is the left region and the center region, and B as the center region and the right region, so that A and B intersect in the middle. And what factorization of the variance says is that the variance of the union of A and B, so this whole region, is nearly the product, well, upper bounded by nearly the product, the sum of the variance on A plus the variance on B. Okay, we'll see in the next slide why this is a relevant quantity to look at. But in 2 lines, what you realize is that then you can...
Sorry, there's a couple questions in the audience.
Yes.
Yeah. Hi, Michael. Sorry for interrupt. Can you go back to the previous PPT? I have a small more question about the gap to decay of correlation. Yeah. So for the Lip-Robinson bound, should you have exponential VT instead of minus VT?
Yeah, sorry. There are
Okay,
there,
good.
there might be typos. Yes, you're right. It's exponential VT. Sorry.
Okay, thank you.
Another question. So throughout this circle, are you going to distinguish between the results obtained from gap and from log Sobolev, or they actually imply each other?
I'm not going to discuss log Sobolev because it's too involved.
Right. Okay. So
I'll only discuss
completely
gap.
out of this circle.
Yeah, it's well, yeah. So there's another circle that involves log Sobolev,
Right.
but
Okay.
and the
Yeah.
intuition is a bit the same, but it's technically much more challenging.
Okay. Great. Then the next slide.
Yes.
And what is epsilon?
Yeah. So I'll get to epsilon in a second. For now, take it as a definition. So what I want to show is that factorization of the variance gives you gap. So for now, just assume that
I have another question. Sorry. So what is the variance of A? I mean, here, what kind of boundary condition you specify, or but because on the right hand, right? Is this like a something? So you specify the interface, or
the way you should understand it as projecting onto the Gibbs state inside of A. And minimally messing up the boundary. In the quantum setting, I'll get to that later, it's a PETS map. It's a PETS recovery map. So you can think of the conditional expectation on A as a PETS recovery map on A.
So it's conditional what's most likely to happen on the boundary of A, or is it?
Yeah, well, on the outside, but in particular here, it's just going to be on the boundary. I'm intentionally a bit vague about this. All of these things can be described very rigorously, but the notation gets very, very messy, and I want to get to some other stuff later. But this is still the classical result. Good. So then, if you believe this definition of the local gap, and you assume that the blocks A and B satisfy the local gap condition, right? Then you can upper bound the variance of A by the numerator divided by lambda A plus the numerator divided by lambda B, right? Just from variance A, variance B. Then in the next line, you take the minimum of lambda A and lambda B and you pull it outside. And then what you notice, and this is very important, that since LA is a sum of local terms and LB is a sum of local terms, you can regroup the terms such that you have the generator on A union B, so on this whole region, plus, because you're double counting, the generator in this intermediate region. Okay. For intents and purposes, we can think of epsilon as being exponentially decaying. It turns out it only has to be polynomially decaying with a polynomial larger than 2. Say L, so a inverse power larger than 2 or 3. I can't remember the details, but it's a small number. And what you can do is you can actually eliminate this term by a simple averaging trick. So you will take different regions out here, A and B being overlapping, but in different places. And you can get rid of this term out there, or you can reduce it sufficiently that it doesn't play an important role. And what that leaves you with is the variance over A union B is going to have a gap, which is the minimum of the gap over A and B. What that tells you is that roughly, if you take A and B to be roughly the same size, and you take the overlap to be significantly smaller, so say the overlap distance to be a square root or a cube root, then roughly doubling the system almost doesn't change the gap. Right? It increases the gap by a term which is 1 minus 2e, plus something which is polynomially decaying. And if you do this iteratively, you can build up the lattice one patch at a time, just by doing this trick iteratively. And you get that as long as you have a bound on on the gap of local patches of the lattice, then you get a bound on the entire lattice. So factorization of the variance gives you a thermodynamic gap of the process. Log Sobolev works in the same way, but instead of using the variance, you use an entropy type functional, which is related to the relative entropy. And then finally, decay of correlation implies factorization of the variance. So here you have to believe some things I'm going to say, because I'm not going to justify them well enough. And what I'm going to say is that the conditional expectation on A of F is going to be the identity on A, and then it's going to have some value on the complement of A. And similarly for B, okay? So if A union B is the entire system, okay, so where there's no boundary outside, what you realize is that E of A, EA of F, even if F is defined on the entire lattice, EA of F only has support on the right-hand side, and EB of F only has support on the left-hand side, okay? Which means that the covariance of AUB, if AUB is the entire system, of EAF and EBF is going to be exponentially decaying if you have decay of correlations, right? Because the left-hand side and the right-hand side have no support, and they have a distance between them, which is going to scale as well, some power of the volume. What you can show by a little bit of algebra is that this relationship is the same as factorization of the variance, okay? And that's the essence of the proof. A very, very important ingredient, which is missing here, is the fact that this argument holds only if A union B is the whole system, okay? Classically, what you can show is that if you define your local gap as the infimum over F and over all boundary conditions of your Gibbs state, what has been shown is that the boundary conditions which saturate this infimum are always going to be product. So the boundary conditions are never going to carry any correlation for classical Gibbs states, which means that you can redefine your lattice with respect to the boundary conditions which maximize these gap relations without creating correlations, and then you can invoke this argument. And this is very important, and it absolutely does not hold in a quantum case. Okay, so that's the essence of the proof. And that's the weak form. In the strong form, you show log Sobolev inequality by showing log Sobolev implies gap. Gap implies decay of correlations. Decay of correlations implies factorization of this entropy functional, and factorization of the entropy functional, again, implies log Sobolev inequality. And it's extremely tight because the factorization of the entropy functional to log Sobolev, or factorization of the variance to the gap, only requires polynomial decay of correlation. But from polynomial decay of correlation, you get gap, which in turn forces exponential decay of correlation. And that's basically telling you that there's no intermediate possibility. It has to be exponentially decaying. So the key ingredients, there are many key ingredients.
Can you comment on what's the difference between the weak and strong here? I sort of didn't get this.
Yeah, so the weak form only gives you polynomial mixing time, and the strong form gives you logarithmic mixing time in the volume.
Thank you.
Okay, so the key ingredients now are detailed balance of the generator, variational characterization of the gap, or Poincaré inequality, LP norm interpolation, variational characterizations of log Sobolev, if you're going for the strong mixing, We require locality of the generator. We used it in Lieb-Robinson bounds and in the trick with the factorization of the variance. Then we require a local conditional expectation on a lattice. If the conditional expectation is not local on the lattice, you can't use it. And finally, we need this local product boundary conditions. And you might ask, which one of these do we know how to manage in the quantum setting? And already a decade ago, first by the work of Zegarlinsky, and then Kristen and I completed it, there's a definition of LP space, quantum LP spaces, with interpolation and all the properties that you might expect. We have a variational characterization of the gap in Poincaré inequality. Similarly with log Sobolev. We had detailed balance of L and locality of L, meaning we knew of a generator in the quantum setting that was detailed balance and local, but only for commuting Hamiltonians. And the big thing that's happened in the past year is that we finally found a quantum generator, quantum Lindbladian, that both satisfies detailed balance and has quasi-local terms. And that really has been an important breakthrough for the community, at least for the mathematical community. Local conditional expectations on the lattice, we do know how to build them for commuting models, but we have no idea for non-commuting models, and local product boundary conditions don't even hold for commuting models. So what we need for a proper, well, I'm basically repeating here, what we need for a proper quantum extension of this theorem is going to be non-commutative LP spaces, mixing time bounds. We have that, Lieb-Robinson type bounds, we have that. We now have an explicit construction of a detailed balance quasi-local Lindbladian also for non-commuting Hamiltonians. The next steps would be to get a quasi-local expectation, conditional expectations, and decaying boundary conditions. So I want to say a little bit more about these steps for the next half of the talk. There's by now a pretty standard classical to quantum mapping. Obviously, Hamiltonians, we know how to define quantum mechanically. Similarly with Gibbs states. Tacitly, I'm always assuming a large finite lattice. The weighted inner products can also be simply defined, typically in the symmetric form. Non-commutative LP norms are defined in this manner. We're not going to use, you're not going to need to memorize this particular form, but they do exist. And the notion of detailed balance also exists. This in particular is KMS detailed balance. This quantum Glauber dynamics, we now understand that there are a couple of different forms of it. I'm going to use what I consider the most elegant and simplest form, is very, very close to a Davies generator in that it's a standard Lindbladian form, so with Lindblad operators. This is work mainly driven by Anthony and Andras, which I was also involved in. The Lindblad operators or jump operators are given by a type of operator of weighted operator Fourier transform of the bare jump operators. The bare jump operators can be understood as this exploratory process in the Glauber dynamics. And this G is related as the Fourier transform of the square root of the Bath spectral function. So sorry, the gamma here is the Bath spectral function. So it says something about how correlations dissipate in the Bath. A are typically going to be local couplings between the system and the Bath. For spin systems, they're typically going to be taken to be the Pauli operators on local sites. That would be the quantum analog of flipping a spin. And the major realization was that as long as this term, the LA rho LA dagger, as long as that term satisfies detailed balance, and this is guaranteed by this construction, you can always find a Hermitian operator Q that guarantees that the other two terms together also satisfy d-tab balance, which in turn means that the entire Lindbladian satisfy d-tab balance. And the specific form of Q is given by this. It's not too important right now. The main thing that needs to be retained in all of this is that for choices of gamma which satisfy d-tab balance, and the only requirement you need on gamma to satisfy d-tab balance is that it satisfies this relationship, also guarantees that the L are quasi-local on a lattice and that Q is a sum of quasi-local terms on the lattice. And that is really quite remarkable. So we have the dynamics now. And these dynamics have nearly all of the properties that we expect and hoped for from classical Glauber dynamics. They satisfy d-tab balance exactly. The coherent and dissipative parts are quasi-local, meaning that they're local around the bare jump operators A and have exponentially decaying tails. Each individual term, each local term or quasi-local term is frustration-free. As long as the A sub A span the entire algebra of observables, then the Gibbs state is the unique stationary state. And I'm not going to talk about this, but unrested, a single time step of the evolution of L is efficiently simulable on a quantum computer. So really mirroring all of the nice properties of Glauber dynamics. In the commuting case, the situation simplifies quite significantly because you go from a sum of quasi-local terms to a sum of strictly local terms. And the reason that terms become strictly local is pretty obvious here. If H if a Hamiltonian is a sum of local commuting terms, then all of the terms not overlapping with site A fall out of, or cancel out from one side or the other of the exponential. And then you get an operator which has support basically right around the site A. And similarly for Q, you get Q is a sum of exactly local terms. And then for those of you in the audience that are familiar with Hamiltonian complexity, if you map L onto a linear operator, right, by doubling the space, then L hat, which is now a large matrix, is simply a frustration-free local Hamiltonian. And the gap of L maps to the gap of H. I guess you want a minus in front here. And then the ground state of L hat is going to be the square root, well, the state associated with the square root of the Gibbs state, or the thermal field double state. So in a sense, this problem of Gibbs sampling and rapid mixing is intrinsically related to the problem of Hamiltonian complexity and determining gaps of Hamiltonians and correlations in Hamiltonians. Furthermore, this funny factorization of variances condition that we had earlier, you can show essentially reduces to the converse detectability lemma from Hamiltonian complexity. So what looked like a very exotic condition actually turns out to be a very familiar condition in Hamiltonian complexity. There are differences between the two settings, in particular that the projections, the local projections, or even global projections onto the ground state preserve the norm of the state in the Gibbs sampling setting and don't in the Hamiltonian complexity sampling setting. So there's more structure here, but many things hold in common. I have not yet, and I don't think anyone has understood what the analog of log Sobolev inequality in the Hamiltonian complexity setting is. That's or even if it makes sense to talk about that. So let's get back to these conditional expectations. This is one of the big things that is missing in the non-commutative quantum setting. So the desired property of a conditional expectation, also called a coarse graining map in the quantum setting, is that E is completely positive in unidal, or CPTP, but in the Heisenberg picture. E satisfies detailed balance with respect to the Gibbs state. And then E on a specific region has to be quasi-local around the region. So do we know of any conditional expectations that have these three properties? Well, in the case of commuting Hamiltonians, we do. Okay, and that we know at least of two. So the first is the Petz recovery map. So the Petz recovery map is given by, so this trace with a big T means you trace on A and you replace it with identity. So trace out A, so the trace over A times gamma AF, gamma A dagger, and gamma A is the reduced state on A. Sorry, it should be the reduced state in the complement of A. So you trace out A, and you leave rho. So the way to understand this is that on A, you get roughly the Gibbs state coming from rho 1/2, or square root of the Gibbs state coming from rho 1/2. And off A, you're sort of canceling out the Gibbs state with this term. Of course, it's not a perfect cancellation, right? Because since you're tracing A out, right, you're doing something with the boundary of A. In the case of commuting Gibbs samplers, just as for the jump operators, the terms in the Hamiltonian which don't touch the boundary of A completely cancel out between rho AC and this rho. Okay, so in the end, you have an operator which only acts, so this whole operator only acts on A. Furthermore, if you take the limit of t going to infinity of the Davies map or quantum Glauber dynamics for commuting Hamiltonians on restricted to a certain region A, again, you get a conditional expectation. And on top of that, that one's projected, meaning if you apply it twice, you get the same back. Generally, in the quantum setting, you also get this relationship that the covariance over AUB, which is defined in this particular manner. Well, it's a consistent definition to define the covariance in this way, meaning that in the commuting case, when you have locality of the conditional expectations, this type of factorization of the variance is sufficient to show gap of the Gibbs sampler. Okay. What's missing is this other step, which goes from decay of correlation to this factorization of the variance.
Hi, Michael.
Yes.
I have a question about the quasi-local properties of the conditional expectation. So,
Yes.
using the current technique, I assume we rigorously need the conditional expectation is a local instead of quasi-local. Is that right?
Yeah, so I think in the non-commuting case, quasi-local would be enough.
But
for commuting Hamiltonians, it's exactly local.
Yeah, so I guess the quasi-local instead of local is a big problem in the non-commuting case, and this is why people come to the non-commuting case,
right? So as it stands now, we don't know how to define a conditional expectation which is at all local.
Okay, I see. Okay.
So quasi-local would be fantastic. But
Okay,
we don't have that, and we're very, very far from that, actually.
Okay,
that's the content of the next slide. Because the existence of a quasi-local conditional expectation actually is the same as the global Markov property. The global Markov property says that the conditional mutual information between A and C, whenever A and C are intersected by B, is decaying exponentially. Well, it's poor choice of constant. So this C is not the same as that C, it's just a constant. Is decaying exponentially in the distance between A and C, or the minimal distance between A and C. That's what we'd like. If we had this strong property, that would guarantee the existence of a local conditional expectation. Unfortunately, and then there are various notions of Markov property, right? This is the strongest, but in this recent paper, I forgot to write the author, but it was a seminal talk at the QIP last year, where the author defines the global Markov property, a local one. So the global one allows for A and C to be proportional to the volume. The local one allows for at least one of A and C to be of constant support. And pairwise is where both A and C are constant support. In order to use conditional expectations in the proof for Gibbs sampling, you need the global Markov property. And the author, I think it was Kitahawa, I'm probably saying it wrong, spent 114 pages proving this local Markov property. I think it's a very, very, very difficult problem to solve. So there really is, this I think the take-home message is this is a very important thing to settle, at least mathematically, and it would have important implications for the theory of quantum Gibbs sampling. The boundary is also very interesting, okay? Because even in the case of commuting Gibbs sampling, where the conditional expectation is local, you're going to get cancellations. Again, this is the complement of A. You're going to get cancellations far away from A, but wherever the Hamiltonians overlap with the boundary of A, you're still going to have terms outside. Okay. And these terms outside are going to give you a type of boundary state. And this boundary state can have correlations, and the correlations can be conveyed through the bulk. Okay. So suffice it to say that there can be correlations at the boundary here, and probably are most of the time. And in particular, we know of examples where we have correlations, and these are topologically ordered models, right? So for instance, the 4D Tor code is going to have extensive correlations in the boundary for the Petz recovery map. So we still don't know, even in the commuting case, how to do that final step of the proof, going from standard decay of correlations to separation of the variances. Now, in the final minutes, what I want to take is a detour to tensor networks. Okay, so up until now, we've only talked about Gibbs states. But I said that there's this connection to Hamiltonian complexity. And this connection to Hamiltonian complexity gets really interesting when you talk about tensor network states, in particular PEPs on a 2D lattice. Okay? Because for PEPs on a 2D lattice, the separation of variances reduces to a property of products of projectors. Okay? What it says, and these conditions are really equivalent in the case of ground states, the frustration-free Hamiltonians, is that if the projector on a region ABC, I guess I didn't try ABC, so on ABC where B intersects A, is roughly the same as a projector on AB times a projector on BC, okay, then you can show gap of the parent Hamiltonian of the PEPs. And this was known from the theory of Hamiltonian complexity. What's interesting is that this condition relating the projectors in PEPs maps directly to a condition on the boundary states of PEPs. Now, the boundary states of PEPs are extremely well defined. It corresponds to taking a PEPs on a lattice and leaving the virtual legs sticking out. Okay. And then you contract the lattice, the physical legs of the lattice with themselves, right? And then in the end, what you have is two pairs of virtual legs sticking out. It's a bit easier to think of it in the MPS setting, where you contract the physical indices, but you're left with some virtual indices. And then what you want to interpret this object, this resulting tensor as, is a density matrix going from the bottom two legs to the top two legs. And you can think of the same in the PEP setting, where now it's a one-dimensional density matrix. Now, what we know, and we call this density matrix the boundary state, and it really does have the interpretation of a boundary state. Now, what we know is that if this boundary state is a local Gibbs state, then it's sufficient to show this condition. Okay. So in the special case of PEPs, this notion of boundary correlations you can show really is intrinsically related to the separation of the variances. And even furthermore, it gives you a type of rigorous bulk, but potentially if you can complete the picture for PEPs. In particular, we have no idea how to go from decay of correlation of the PEPs to this Gibbs property at the boundary. But if we could, this would give a rigorous bulk boundary correspondence in condensed matter physics, which would really be remarkable. And so that sort of closes the geographic picture of this question of mixing and in time and space for Gibbs sampling. But I think the PEPs question is just as interesting. So summing it all up, what do we know? In the commuting case, we know a great deal. We have a proper description of the generator. We know that it's rapidly mixing in high temperatures. This is results by any combination of Angelo Capel, Combis Rouset, Daniel Slick-Franca, and Yvon Bardet. We know that it's rapidly mixing for one-dimensional systems. We know that regular decay of correlations implies mutual information decay. So a lot of these relationships, these extended web of relationships have been extended for commuting cases, at least in 1D and at high temperature. We also know rapid mixing for some specific models in 2D, in particular the toric code. And I'd say we really strongly suspect that this entire map of equivalences can be established in 2D, even despite this small gap in the proof. In the non-commuting setting, I think it's completely open. So we finally have a description of a quasi-local generator. We know that it's rapidly converging at high temperature. I think only poly converging at this point, but I'm sure that it'll be possible to get log Sobolev convergence as well. In 1D, it hasn't been shown, but I'm quite confident it can be shown. Same with mutual information decay. When it comes to rapid or torpid mixing of specific models, I think this is very much still open. We basically know nothing about non-commuting models in more than one dimension. And I think it's also extremely uncertain whether this whole program can be closed and completed in any satisfactory way in the non-commutative setting. I think it's a great challenge, but it's certainly very hard, and I think it's very unclear whether it at all holds, right? Because in the end, these boundaries really are very quantum mechanical, and they can have a lot of dynamics in them themselves. There could be boundary phase transitions, all sorts of things happening that really are not possible classically. It's important to note that these results do have a lot of applications, or at least connections, to other areas in mathematical physics and in quantum information. So clearly, from the topics of the workshop, the quasi-local generator is closely related to quantum simulation problems. And I expect a lot of the other talks are going to be discussing this connection. This rapid or torpid mixing of specific models brings back this old dream that we had a decade ago of a self-correcting quantum memory, right? The analysis of a self-correcting quantum memory really is all about the analysis of these non-commutative Gibbs samplers. And just recently, there's been an important advance for self-correcting memories, which is that there's specific continuous variable systems, so GKP type Hamiltonians, which have been shown to be self-correcting and are non-commuting. It seems subsystem code properties play a very important role in that example and could play a very important role for spin subsystem codes. And this thing about the equivalence holding or not probably is going to boil down to some very fundamental bulk boundary correspondence, which is of great interest both in condensed matter and high energy physics. So somehow the Pandora box is really open, and there are many, many, many interesting questions, both practical and mathematical, to look at. Thanks for your attention.
Great, thank you. Any questions?
Hi, Michael. I think for the non-commuting Gibbs samplers, one of the most important questions is that how you define a local gap. For commuting Gibbs samplers, we know that the link binding is exactly local, and it's easy to define what's the local gap. But for non-commuting ones, because that each local region has an exponentially decaying tail, so I think if you consider the Hamiltonian of a local region, then I believe it has exponentially many of exponentially small eigenvalues. So it's hard to define what a local gap is.
So I think we know what the definition of the local gap should be. So you can define the conditional expectation value as being the infinite time limit of the Lindbladian restricted to region A. Okay, and that's a well-defined quantity, and you know the kernel is going to be well behaved.
Oh, okay.
Right?
So the local expectation.
But what you don't know is whether that quantity is local, right?
Okay. Yeah. So the local expectation, local conditional expectation is just the projection onto the low energy spaces of the parent Hamiltonian. If you look at it from a parent Hamiltonian perspective, so it's just So
it could be, and well, I'm not sure, right?
In the commuting case, this is true.
In the commuting case, that's the case, but maybe that is not going to lead to a local conditional expectation, but there might still exist local conditional expectations, right?
Yeah. Okay. Yeah. Thank you.
Questions? If there are no more questions, let's thank Michael again. Thank you.
Thank you very much.